Page 409, exercise 30 says approximate the area under the graph of g of x equals 0.1 x cubed plus 1.2 x squared minus 0.4 x minus 4.8 over the interval -10 to -4 using 6 subintervals. Here's a picture of this, of what the question is asking. If you were to graph this function, which would take a while, you eventually would come up with this. This is the graph of g of x equals 0.1 x to the third plus 1.2 x squared minus 0.4 x minus 4.8. Notice negative 4.8 is where this curve crosses the y-axis. So the question is to approximate the area under this blue thing in the interval from -10, which is here, -10, up to -4. When they say the area under the graph, they really mean between the function and the x-axis. So just this part of the function, this curve. So we're looking for the area of this region that I outlined in green. The area means the number of these squares. This grid, this graph paper has all the squares all over the place. This is 1 square unit that I'm coloring in. The area of the region means how many of these are enclosed in there. And you could go ahead and try to count them. But to approximate the area using 6 subintervals, here's the procedure. First of all, we're going to make, when it says 6 subintervals, that means we're going to make 6 rectangles. The phrase 6 subintervals means I'm going to be drawing 6 rectangles. And here's an important formula right here. Right here. Delta x, change in x equals b minus a over n. That is going to be the width of each rectangle. So in the question, I see that I need 6 rectangles. And b minus a over n is always the width of each rectangle. And we call it the change in x because we're going to make this table a table of x and g of x. The first x is going to be the first x that's given. And delta x, b, by the way, these two numbers are called a and b. A is -10 and b is -4. So b minus a over n, the number of subintervals is n. In this question, b minus a over n comes out to be 1. Positive 10 minus 4 divided by 6 is 1. So we start at -10 in this table, and x gets changed by this amount. The change in x. Delta x means the change in x. So change -10 by this amount, and it becomes -9. Change -9 by that amount, and that becomes -8, and so on. We keep changing x by this number until we get to the b. Start at a and stop at b. So if we were to plot these points, they would form the curve. So I'll just highlight these points on the curve that's already there. There's the point -10, whatever, -9, whatever. So here's how we draw the rectangles. We start at -10, go to the curve. Right there, we go delta x units to the right with a flat line segment, and then drop a vertical line segment down. Then at -9, we go to the point on the curve. This is the blue curve. Drop a vertical line segment all the way to the x-axis. Go horizontally to the right 1 unit because delta x is 1. And go all the way down to the x-axis. -10, -9. At -8, we go to the point on the curve. Wherever we are at the curve, make a flat top 1 unit wide. That's the width of each rectangle. And straight down to the x-axis. Go to -7. Hit -7, find the point on the curve. Go to the right and down. I think I forgot this one right here. So I got one more. Start hit right here at -5. Here's the point on the curve. So you should see 1, 2, 3, 4, 5, 6 rectangles. They're slim rectangles. All we're going to do is find the areas of all these rectangles and add them up. That'll answer the question. That'll approximate the area between the blue curve and the x-axis from in the interval from -10 to -4. So the approximate area they're talking about is going to be how wide each rectangle, or how wide the first rectangle is, times how tall it is. How tall it is this number right here, 19.2. The second rectangle has width 1, and the how tall it is 23.1. Each rectangle's area is the width, which in this case they're all of width 1, times the length. The length is the y value. The next one is 24. So it's 3, got 3 more to go because it said 6 subintervals. The fourth rectangle, 1, 2, 3, 4, has width 1 because they all have width 1. And the length of the fourth rectangle is 22.5. One, 2, 3, 4, 5. The fifth rectangle has width 1, and the length is 1, 2, 3, 19.2. And the last rectangle, because there's going to be 6 of them, 1, 2, 3, 4, 5, 6, has width 1. And the length of that last rectangle is 1, 2, 3, 4, 5, 6, right there, 14.7. So these are the areas of these 6 rectangles. Each one is how wide times how tall. They all of them have width 1. That came from the width of each rectangle comes from this formula. The lengths of all the rectangles are these numbers here. Please notice we did not use that number. It's part of the function, but it's not the height of any of the 6 rectangles. We're supposed to be using 6 rectangles according to the directions. So do all this multiplication, very easy because they're ones. You get the areas of all these skinny, tall rectangles and add them all together, and the total comes out to be 122.7. That's the answer. I'm going to rewrite it a little more neatly. 122.7 is approximately the area between the blue curve and the x-axis in the interval from -10 to -4. That's it. Now, in calculus, we have a way of calculating the area exactly, and it goes like this. If we make skinnier rectangles so that we could fit more of them in here, instead of 6 rectangles, maybe we could make 60 rectangles, and then each one would be really, really, really skinny. And then the accuracy would be better. Obviously, the areas of these rectangles is not exactly the same as the area between the curve and the x-axis. But if we could make 60 rectangles or 600 rectangles, then the accuracy would get better and better. So the following is the definition of what we call the something called the definite integral. Each rectangle in the picture I just drew had for its height the value of the function. And I'll put an I subscript because they were all different ones. The f of x, which was the height of the rectangle, was different for each rectangle. But we multiplied each of those lengths by how wide the rectangle was, which was delta x. So this represents how tall each rectangle was. This represents how wide. When we added them all up, the symbol sigma means add all of them up, from I equals 1, meaning the first rectangle, up to n, which in the example we just did was the 6th rectangle. That's how we got the approximate area. In front of this, we put the limit as n approaches infinity. The n is the number of rectangles. If we make those get more and more and more, then we have what we call the integral of the function. And the delta x magically becomes dx. Delta is a Greek letter. D is kind of the same letter, but not Greek. Delta D. And attached to this integral symbol, we put where the region started down here and where the region ended. And that always equals capital F evaluated at the number up here minus capital F evaluated at the number down at the bottom here, which in the problem we just did, those numbers were -10 and -4. And important thing, this capital F, the derivative of that function, is the integrand that's up here. So we'll now demonstrate what this is all about, because right now it looks mighty complicated. So we're not going to actually find the exact area. We just got an approximation a little bit ago. It was 122.7. So the area between this function and the x-axis from x equals -10, right here, to x equals -4, if you count up these squares, there should be about 122 of them, close to 123. If you want to know exactly how many there are, we do this. We say the area of this region that I'm shading here, the area of that green region, we call it the integral of this function, which is 0.1 x to the third plus 1.2 x squared minus 0.4 x minus 4.8, because that's what we use to find the heights of every rectangle, dx, because dx is how wide every rectangle is, and attached to this integral symbol, we put where this region starts, the x value, and up at the top we put where the region ends. Next thing I do is I take this integral symbol and distribute it to each of these terms. I write the integral of 0.1 x to the third dx. Each of these terms is going to get this dx attached to it separately. Plus, so I'm on the next term now, so I 1.2 integral x to the second dx. These attached numbers, I'll worry about those later. Third term is negative 0.4 integral x dx. And there's one more term, negative integral 4.8 dx. So 1, 2, 3, 4 terms. 1, 2, 3, 4 integrals. For each term, I put the constant, 0.1, 1.2, negative 0.4, negative 4.8. All of those go to the left of this symbol. Also, each term gets a dx, 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 because we also distribute the dx. So the constant that's multiplied, 0.1, just gets brought down. And the integral of x to any number, dx, is x to that number, the exponent, plus 1 over n plus 1. And the plus c that we used earlier will not be used in these. Whenever we have a definite integral, that means numbers are attached, we leave out the plus c. The integral of x to the third dx is x to the fourth over 4. Copy the plus, copy the 1.2. The integral of x to the second dx is x to the third over 3. So the integral symbols and the dx's are disappearing now. Copy the negative 0.4. The integral of x to the first dx is x to the second over 2. Copy the minus, copy the 4.8. And the integral of dx is just x. Then, instead of plus c, which we did when we did the indefinite integrals, instead of plus c, we put a bracket with the two numbers attached, negative 5 up here and negative 10 up down there. When we put the bracket there at the end with these numbers attached, that means everywhere there's an x, we put this number. After I do that, then I'll tell you what we do with the negative 10. So I'm writing 0.1 times negative 5 to the fourth over 4, because you can extend this line, plus actually, I think it was supposed to be from negative 10 to negative 4, wasn't it? So hang on, I'm going to fix this all. That was supposed to be a negative 4. Didn't need that yet, so it's okay. That's supposed to be a negative 4. So everywhere there is an x, I'm putting negative 4. Plus 1.2 times negative 4 to the third. This is all over 3, because you can extend that. Minus 0.4 times negative 4 to the second over 2, minus 4.8 times negative 4. After all the x's are replaced with this number, then we say minus the quantity, whatever you get when you replace x with negative 10. So I'm going to try to shrink this so that I can fit it all on there, because it will be hard to follow what I'm doing. I don't know if I can do it, but I'm going to try. All right, so check out where I am so far. So in this, which we call the antiderivative, we replaced all the x's with negative 4. After the minus and this opening bracket, we're going to replace all the x's with the number that's down here, like so. Negative 0.1 times negative 10 to the fourth over 4 plus 1.2 times negative 10 to the third over 3 minus 0.4 times negative 10 squared over 2 minus 4.8 times negative 10. So I'll summarize. Here is the antiderivative up here with this number in place of x. That's what this is. Minus, and then this is the same antiderivative over here, but it's with this number in place of x. So now you do lots of arithmetic with your calculator, and I'll just take a second to do that and tell you what you should get. So you can check this if you want. I just did all of this on the calculator, and I got 118.8 exactly. So that's the truth. 118.8 is really the exact number of square units, that's these things, that are inside this shaded region. 118.8. So our approximation before, when we made the 6 skinny and tall rectangles, we got 122.7. That's pretty close, but it's a little over, because see how these rectangles, some of them are a little too tall to be the actual area between the curve and the x-axis.